a supervised machine learning classifier model for binary classification problems. SVMs are one of the most popular prediction models around, and it continues to be despite competing algorithms like deep learning models, especially for problems with limited data sets. So if you don't have a lot of data, you can't really use those deep learning models. They will not give you good performance. They won't even train properly. That's why we are forced to learn, or we are forced to use methods from CS280. So there's a difference between CS280 and CS284. CS284 will not make CS280 obsolete because the methods we learn here are still very useful, especially in cases where we have little data. SVMs are based on statistical learning theory, which provides a solid mathematical foundation for the method. Shortly after the SVM was proposed in the mid to late 90s, it became known as the neural network killer due to its very good performance, in fact superior performance compared to the neural network. And also it has that nice mathematical property of being globally optimal. Let's take a look at the history of the support vector machine. So in 1963, Vladimir Vapnik and his PhD advisor, Alexander Lerner, introduced the generalized portrait model, which is the precursor of the SVM. Unfortunately, during that time, despite this progress, hardly anyone outside the USSR have actually learned or examined this algorithm, because that was during the time of the Cold War. And the Americans and the rest of the world can't read Russian, so they just didn't learn that there was also progress in Russia at that time. So SVM is the linear version of the generalized portrait algorithm. In 1964, Mark Eiserman and his colleagues introduced the geometric interpretation of kernels as inner products in feature space. The following year, in 1965, Cover introduced the large margin hyperplanes. In 1974, Vapnik and Chervonenkis started working on statistical learning theory. And the culmination of their work was this paper in 1992 by Vapnik and his collaborators, where they described or presented the support vector machine paper at the COLT conference. 3 years later, in 1995, another collaborator of Vapnik and he himself presented the soft margin classifier, which is the subject of today's lecture. And also in the same year, Vapnik introduced the regression version of SVM. So before we continue, let's first talk about parametric and non-parametric classifiers. So parametric classifiers are classifiers with a fixed number of parameters. And these parameters, the number of parameters, are independent of the size of the dataset. For example, your MLP. So the number of weight vectors, and elements of your weight vector are fixed regardless of how big or how small your data set is. And you're familiar with the naive Bayes? The same. The number of parameters is fixed, independent of the size of the data set. So the data set is the one that determines the values of the parameters, but not the size of the parameters. The number of parameters. So you have following as examples of your parametric classifier: logistic regression, linear discriminant analysis, the perceptron, and your MLP, as well as naive Bayes classifier, plus many others. The parametric classifier is usually characterized by being fast compared to their non-parametric counterparts. On the other hand, the non-parametric classifier has a flexible number of parameters, and this means that the number of parameters grow with the data set. If there's a large data set, then the number of parameters also increase. However, the advantage of the non-parametric classifier is that it has fewer assumptions regarding the nature of your data. So while here, in the case of the parametric classifier, you have the assumptions like say Gaussianity and the like, depending of course on the classifier. But for example, for the naive Bayes, there is that assumption of independence, right? Feature independence, which is actually violated in many applications of the naive Bayes. The feature independence requirement, or the feature independence requirement, is actually violated, and yet it still gives you a good performance. So in the case of the non-parametric classifier, again, there are fewer assumptions about the feature distribution, the independence of features, and the data distribution. Examples of non-parametric classifiers are the k-nearest neighbor, decision trees, and today's support vector machines. For the KNN and support vector machine non-parametric classifiers, part or the entire data is carried along with the algorithm after training. While for parametric classifiers, the data may be deleted after the parameters have been computed. So in the case of naive Bayes, you determine the conditional distributions, the values of those probability vectors, and that's it. You can throw away your data. You can now use the trained naive Bayes classifier for classifying spam or ham and so on. But for the KNN, especially for the KNN, you need to carry around that data. So those data points are crucial. You cannot throw them away because they are actually important in determining the class of your query. So here's a diagram. These are two diagrams illustrating the difference between the artificial neural network and the support vector machines. So the ANN is familiar. You studied this last time. Now, when you train your artificial neural network, the requirement is that we want to minimize the number of errors, misclassification errors. So what we want to do is to have all the points belonging to one class on one side of the hyperplane and all the other points on the other side of the hyperplane. So looking at this diagram, you can see that this red line here is a good, by artificial neural network standards, is a good hyperplane, and so is this green line and the blue line and the yellow line. In fact, there are an infinite number of possible hyperplanes that can classify the two sets, the two classes of our data set correctly. So with zero error in this case. No? So, however, we know that there are better hyperplanes. In fact, there is what we call the optimal separating hyperplane. So this is the optimal separating hyperplane for these two classes. So this green broken line here is the optimal separating hyperplane. Why is it optimal? Because it is maximally distant from all the points of your data set. Okay? Maximally distant. So that is the property of the support vector machine. It gives you the optimal separating hyperplane. And that's the reason why when the SVM came out, it killed the ANN. So people started moving away from ANN and started using SVMs. So for more than a decade, maybe 15 years or so, people were using SVM and not the neural network. And if you're a computer scientist and you insist on using ANN, people look at you and they would judge you and think that you are using an obsolete method, which is not optimal. And they are correct. So the SVM, even up to now, is still a very good algorithm. In fact, I would use it for, of course, for problems with not so many data points. So it's still very good. Still a to-go algorithm up to now. And I encourage you to use the SVM. So I gave you an assignment, a programming assignment, which will show, it should illustrate how good the SVM is. Of course, it's not really fair because you'll be using an implementation that's already production grade, while the ANN that you'll be working on is your own. So maybe it has bugs and so on, but still, it gives you an idea of how different they are. So even if you tweak your ANN very well and put the two side by side, the production version of the ANN versus the production version of the SVM, you will see that in most cases, okay, not all, of course, in most cases, the SVM performs better than your artificial neural network. Now let's start by talking about linear learning machines. So here we have the following classification problem. We would like to find a mapping F that takes in as input X, and that X is a vector in L dimensional space. Okay, it is L parameters, and maps it to a real number. Now F defines the separating hyperplane that assigns the input X to a positive class plus 1 if f of X is greater than or equal to 0, and a negative class minus 1 if f of x is less than 0. So this is not a 0, 1 thing. This is a plus 1, minus 1 classification problem. Now, the form of f of x is the following. It's w transpose x. So you take the dot product of your weight vector and your input, and you add a constant b. Okay, so that's the matrix notation. Now, if you want this expanded notation, then this is how it looks like. So here, the classifier, okay, would have a w vector. We have this vector consisting of L elements whose values may be real numbers, any number in a real number, and B as well. So the same, B is the bias. So these are the parameters that are learned from data during training. Now there are L plus 1 parameters. Why plus 1? Because you have a bias here. So there are L plus 1 free parameters that will represent all the possible hyperplanes in R L. Now for SVM, we would like to develop the algorithm. For this algorithm, we have the following intuition. For all positive examples, y equals plus 1, it is nice to have that this f of x, the value of f of x, or w transpose x, including the bias. We have absorbed the bias here, so just we can do that by setting the x0 to 1 and then the w0 to, well, to one of the elements. So any trainable is a trainable value, and this value here should be, we want to have it very much greater than 0. And similarly for negative classes, it's nice to have a function value that is very much less than 0. The more negative it is, the better, and the more positive it is, the better. So by this intuition, we're basically saying that we want to maximize the distance between the hyperplane that we want to determine and the data set. Okay. So our second intuition is the following. We assume first a linearly separable data. We will deal with the non-linearly separable case later on when we talk about kernels. So here, in this direction, we know that this dashed line here separates the two classes also. Okay, but there's this. But if you notice, the distance z1 here, the two z1s here, is smaller compared to the distance z2 here. So you'd want to get the direction, the second direction, which will maximize z2. So the intuition, this intuition is basically doing that. So you want this this gap to be as maximum as possible. So the hyperplane in the second direction is best because it is farthest away from the data. Am I recording?
Yes, sir.
Am I?
Yes, sir.
Yes. Okay,
Yes,
good.
sir.
Okay, good. So since this hyperplane is the best one, and there's only one best hyperplane, it's called the optimal separating hyperplane. So this hyperplane is unique for this linearly separable data. Now, how do we get this hyperplane? So that is what we want to do here. We want to write some equations that will help us arrive at this hyperplane. Let's first define the so-called functional margin. So if we want our classifier output to be +1, if our output, our desired output is +1, we want W transpose Xi plus B to be very much greater than 0. And similarly for the case where our label is -1, we want this quantity to be very much less than 0. Now, you can actually combine these two in this manner. So for example, so yi is positive here, and then we want it to be very much greater than 0, so which means this quantity is also positive. Now, if we want this quantity to be labeled -1, and this quantity is also very much less than 0, then the product of yi and this quantity must be greater than 0. In other words, if the product of our label, which is either 1 or -1, times this function here is greater than 0, then what we have is correct classification. And not only that, we want this to be as big as possible, the one on the left hand side. So now we define the functional margin of an example xi, yi with respect to the hyperplane WB as the quantity gamma hat of I equal to this quantity here, the label plus or -1 times W transpose Xi plus B. So that's our functional margin. That is for just one example. Now we are not just interested in one example. We want to have the functional margin for the entire training set. So now we define the functional margin distribution. The functional margin distribution of a hyperplane with respect to a training set this time is the distribution of the margins of the examples in S. So so how this what are the values of gamma hat I for all i's. So if you have a big N examples, then you have gamma hat 1, gamma hat 2, up to gamma hat big N. Now, so we have the functional margin for the distribution. What we want is the functional margin for the entire training set. The functional margin with respect to the entire training set is the minimum of the functional margin distribution. In other words, you have gamma hat 1, gamma hat 2, up to gamma hat N. Okay, what is the minimum gamma hat? That is your functional margin. The worst case, we want the functional margin to be large, and therefore the minimum of gamma hat I is the worst case for the entire training set. Now, remember that we have WB as free parameters, and we want gamma hat I to be arbitrarily large, right? We want, if you recall, we want this to be as large as possible, right? We want this to be as large as possible. Okay, this value here, the left hand side, it's not 0. It should be as big as possible. However, these are free parameters. What are the free parameters? W and B. Now, Xi and Yi are fixed by your training set. So since these are three parameters, we can make these two as large as we can, and we satisfy the condition. Okay, so for example, we have a current value of W, current value of B, satisfying the equation above. If we multiply both by 100, then we get a 100 gamma I, so we make it larger. So there's no constraint. So now we fix this problem by using a normalization condition where the W now is equal to 1. In other words, the weight vector should have a norm equal to 1. Okay, so that is, we constrain the weight vector so that W transpose becomes now W transpose over its norm. So in this way, if we do this, impose the condition, then we basically constrain our W to be, and the unit ball, this is a circle, right? This is a hypersphere, okay, of unit radius in some high dimensional space. So we are basically saying that our W must be a point in a hypersphere whose radius is 1. So it's called a unit ball. Now let's take a look at the geometric margin this time. So we're talking about the functional margin. Let's talk about another kind of margin. It's called the geometric margin. The geometric margin is the following. First, we have the normal to the hyperplane, which is, okay, so this is a hyperplane, and this is our W. Now, the normal to the hyperplane is just this W here divided by its norm. So basically, it's a unit vector pointing in the direction, in this direction, this perpendicular to the hyperplane. Now we calculate. Suppose we have a point here X. We calculate the geometric margin. Basically, the geometric margin is this distance of your X. Okay. Could you switch off your? You please switch off your microphones, Mr. Katipunan. We could hear you.
Sorry, sir.
I'll have to mute all of you. Mute all. No. Can you hear me? I might have muted myself also. Hello. Well, just reply via the chat box because I should have muted you. I'll mute you again. Those who attempted to reply. Okay, so I will not allow you to unmute yourselves. Okay, so now can you hear me? But reply to the chat box. Okay, so let's continue. So as I was saying, we have this point here whose distance is Z, and it's called that the geometric margin gamma I for point xi. So please take note of the notation. The geometric margin does not have a hat, so it's just gamma I, while the functional margin is gamma I hat. So they are different. Now at point A, which is the this point here, which is the projection of your point xi on the hyperplane, we have the following. So this point A is xi minus, okay, A is xi minus this vector here, okay. This vector here is gamma I or z, right, times the vector, because this is just a value here. Is that it has to have a direction, and the direction is this, okay, and it's negative because we are subtracting, okay. It's a vector going that way. So at point A, what we have is the following. Now, since point A is on the hyperplane, it must therefore satisfy the condition W transpose XA, which is this whole thing here, okay, XA plus B equals 0. Because all points on the hyperplane must satisfy the equation W transpose that point plus B equals 0. Now, with a bit of algebra, multiply this here, and we shuffle a bit, and you just what you get. So W transpose XI plus B is equal to gamma I, your geometric margin, W transpose W, which is product, divided by the norm W, the norm of W. Now, this W transpose W is just the norm squared. The norm squared divided by the norm just gives us the norm itself. Okay. So this we have the following. So this is gamma I norm of W is equal to this. Therefore, gamma I is just this whole thing divided by the norm, which is now this. So gamma I is W transpose divided by the norm of W times Xi plus B divided by the norm of W. So these values in the denominator are just scalars. Okay. So gamma I is the signed distance of Xi and the separating hyperplane. Okay, so Z, that's Z. Okay, and that is the one that we want to maximize, right? We want to maximize that, not just for this point, but for all the points. So now, more generally, what we have is the geometric margin for both classes. Okay, so this is just for this. Now for the other class, we can write the following. So W of gamma I is equal to Wi, Yi rather, which is your label, times this quantity. Now, if we compare this, okay, if we compare this with, this is the geometric margin equation. Now, if we compare this to the equation for the functional margin, what is the difference? So remember this? This is our equation for the geometric margin, this one. So what is the difference? The difference is that this first term here has a norm under the denominator, and the same here, right? Okay, so the same as before, except that here we have the norm of W, the denominator. Now, if you want to make the two the same, we just impose the condition that the norm is equal to 1. Therefore, we can say that when the norm of your weight vector is equal to 1, the functional margin is equal to the geometric margin. So now, in general, what we have is the following. Okay, So this is true for W, the norm equal to 1. Now in general, this is what we have. The geometric margin is equal to the functional margin divided by the norm of W, which is this. No? So, okay, so nothing special. Now, what we want is let's now define rather the geometric margin of the training set. Similarly, as the previous case for the functional margin, gamma now is now the geometric margin for the entire training set, which is minimum of gamma I. So the geometric margin gamma is the maximum geometric margin over all hyperplanes. Let's go back. We're basically maximizing this z here, right? So the one that maximizes this z is this hyperplane here. Okay, and it's in this direction. So this one does not have a good value for gamma, while this one has the maximum value for gamma. Okay, now let's talk about the maximum margin classifier. The maximum margin classifier is the precursor to our SVM. It works only for linearly separable data, but don't worry, we will extend the same idea later on to make this into an SVM where it can handle non-linearly separable data. So for now, what we want is to design a maximum margin classifier using the ideas that we have described earlier. The ideas of the functional margin and the geometric margin. Let's have the first version, or the alpha version. Like software, so the alpha version. So let's just test whether it will work. Okay, version 0.1. We want to maximize the geometric margin, right? So that's understandable. So in other words, we want to maximize gamma, and we would like to determine the gamma as well as the W and B that will maximize gamma. Subject to the condition that WI W3 transpose X plus B is greater than or equal to gamma. And also the condition that the norm of W is equal to 1. So why do we impose this condition? We impose this condition because we want to make the geometric margin equal to the functional margin. So now, is this a good formulation for our optimization problem? Well, no, it's not a good formulation. Why? Because it has a non-convex constraint. Okay, this imposes the condition that W must lie on the unit hypersphere. Okay, so W must have a unit radius. So this is a non-convex constraint. Now we know that from optimization, if you have a non-convex problem, there's no guarantee of convergence, and also we will encounter local optima problems. But for SVM, we want precisely a a globally optimal solution, and we want it to converge as well. So this is not a good formulation. Let's improve on it. How about maximizing the functional margin this time instead of the geometric margin? So we know that the functional margin is gamma hat over, well, the functional margin is this, but we would divide it by W hat. W by W, okay, norm of W. Okay, so we want to maximize this quantity here again, such that this time it's this yi W transpose x plus v is greater than or equal to your functional margin. Okay, so this is the minimum. Remember, this is the minimum of the functional margins for all the points, right? Now again here we need to apply a scaling constant, gamma hat equals to 1, otherwise it will blow up. It will keep on increasing to infinity and you don't solve the problem because this is a maximization. Okay, now okay, so maximizing gamma hat over W norm W is the same as minimizing W transpose W. So with this, okay, so this is what we need to make this not explode. So with this, we are inspired now to have this formulation, where the final version now of our optimization problem to solve for the right values of W and T is minimize, not maximize because it's equivalent, okay, minimize W transpose W such that this quantity is greater than or equal to 1, where I now equals 1 to n, where n is the total number of points. So now we have a linear constraint here, okay, and a quadratic. This is a quadratic, convex quadratic objective function, and linear constraints. Okay. Now this actually is a very good formulation because we can efficiently solve this minimization problem using what is called quadratic programming. This is quadratic, and there's no local optima. Okay, so let's now embark on that journey to minimize that. And to do that, we need some additional mathematics, okay, optimization mathematics, which is familiar to most of you, most of us. It's really just the following. So this optimization problem has long been formulated by the French mathematician Lagrange. So it's called the Lagrange multipliers. Given an objective function f of x for the optimization problem, minimize f of w, where w is an n-dimensional vector whose elements are real numbers, such that hi of w, h subscript I of w is equal to 0 for I equals 1 to L. So here we are imposing equality constraints. Okay, so this is an equality. So you you want to have another function that relates the variables here in f equal to 0. So this is an equality constraint. Now the Lagrangian function is defined as the following. So we define this special function here called the Lagrangian, and it's equal to f of w, our objective, plus the summation of some constants called Lagrange multipliers times our equality constraints. There are L such equality constraints. Okay. Now, according to Lagrange, okay, we can find the minimum by setting the gradient of L with respect to W to 0 and compute for W star, which is the optimal value for W, and similarly for beta. So beta star is computed by differentiating this quantity here and setting that equal to 0 and finding that value that makes that derivative equal to 0. So more precisely, you have the following theorem by Lagrange. For W star, which is the optimal value, when you see a star here, it means optimal. W star, to be a solution, it is necessary that there exists some beta star such that this gradient is equal to 0, and also this gradient with respect to beta this time is equal to 0. Now, take note that we are optimizing or minimizing this function subject to equality constraints. However, our problem here is not this one. Let's take a look at our problem again. Our problem is here. This is not an equality constraint. This is an inequality constraint because it's greater than here, right? So this is our HI. Right, this is our HI. HI is not. Oh, sorry. HI is. This is not HI. It's GI. Okay. In other words, this is not an equality constraint. This is an inequality constraint, which is now the subject of this generalized Lagrangian function. So, given an objective function f of x for the optimization problem, just like before, minimize f of w. With two sets of constraints, the one that we had earlier, which are the equality constraints, and this time we have another set, which are the inequality constraints. Okay, so we have two sets of constraints. Now we define the generalized Lagrangian function as f of w plus summation of alpha I subscript I g subscript I of w plus what we had before. So this is the one for equality constraints, right? H is for equality constraints. Now for inequality constraints, we have g. For our optimization that we're trying to solve for our SVM, this is 0 because we don't have equality constraints. Now, for this Lagrangian, generalized Lagrangian function, the alphas and betas are called Lagrangian multipliers. Okay, so this is our Lagrangian, our generalized Lagrangian function. Now let us define the maximum of this Lagrangian function. So the Lagrangian function can be maximized, and we would like to maximize it. And the value that will maximize this left-hand side or this right-hand side when we vary alpha and beta, subject to the conditions that the alphas are positive or non-negative, rather, it can be 0. Okay. Is equal to theta p. Take note that this quantity hi we want it to be 0, right? Equality constraints. So, and if we want to maximize this whole thing, we're basically forcing this to be 0. Otherwise, beta will try to also maximize itself in the plus infinity direction or negative infinity direction, depending on the value of this, right? And therefore, blow this up. Okay, so we don't want to have that. So what we want is to, okay, now we have the following problem. So we have defined this quantity here, which is to maximize this value here. Now we want to minimize this quantity, which means that we want to minimize also the maximum of this quantity here. So consider the problem where this is theta p. We want to minimize the maximum of L. Okay, so this is the original or primal problem, right? We want to minimize the maximum of L. Okay, to see that why this is the same as the original SVM problem that we are trying to solve. Okay, recall our original primal problem. Okay, this is our original problem. Now the generalized Lagrangian function, as described earlier, as defined earlier, is just this. So it's a repetition of what we had earlier. So these two. Now, for theta p, which is this part here, if gi, okay, which is gi here, is greater than 0, okay, if gi is greater than 0, okay, sorry, here, if gi is greater than 0, and alpha I is any non-negative number, and you're allowed to make alpha as huge as big as possible, then what happens? When you start maximizing, alpha keeps on growing and growing, and this whole thing blows up. So theta p now is infinity, since you can make alpha I as large as possible. Okay, so when there's a constraint violation, okay, when you violate this constraint, okay, so this is the inequality constraint, and you violate that constraint by making this left hand side greater than 0, then theta p goes to infinity. Now let's take a look at the other one. If, on the other hand, or if there's also a violation in the case of the equality constraints, meaning h is not equal to 0, it's a constraint violation, then it's easy to see also that this quantity here will blow up, because the betas can assume any negative or positive value, and if this is non-zero, this will just keep on increasing and increasing, and then this will happen. Otherwise, theta p is equal to f of w. Okay, so again, if the constraints are satisfied, then we have this. Therefore, for theta p, if the constraints are satisfied, we have the original problem. On the other hand, if it is not if the conditions are not satisfied, there are constraint violations, this whole thing becomes infinity. Therefore, the primal problem, minimum of theta p, is the original problem. So we have actually restated the problem into now a primal problem, which is minimize theta p, and this is the same as our original primal problem, which is this. Now, let's talk about the dual. Now let's define the dual as theta d alpha beta. These are the parameters. But this time we are minimizing the generalized Lagrange multipliers. And we would like to look for the weights W. So let the value that will give us the minimum value of the dual, this one, be equal to D star. So this is the minimum value. And that's equal to the max of the minimum of L. This is just the opposite. Before we were minimizing the maximum of L. But in the dual problem, we are maximizing the minimum of L. So this is the same as maximizing our theta d. So we have again the primal problem, just minimize the maximum of L. For the dual, it's the it is to maximize the minimum of L. Note that the maximum of the minimum of anything is less than or equal to the minimum of the maximum of anything. Therefore, so you can show this mathematically, but I won't show it now. I won't show it to you. You just read up on this if you're not convinced. Then we can therefore say that this star, this quantity here, will have a value that is less than or equal to P star. P star being, where's P star? Being this. Now, under certain conditions, the two values become equal. And we will see what these conditions are. Also, in general, it is better to solve the dual problem because it is a simpler problem, as we shall see for ourselves in a short while. So what is our strategy? Our strategy is to write the primal problem, then derive the dual, and then solve the dual. So that's what we do in this optimization problem. So what are now the conditions for equality of D star and P star? Conditions are the following. Let F be convex. Okay. When we say convex, the Hessian should be greater than or equal to 0. I think we have to talk about this in our first lecture. Or no, it's a lecture, the lecture in linear algebra in 284. Anyway, if you didn't watch that part, then just basically when we say F is convex, the Hessian, or the second derivative matrix of second derivatives, will have it's going to be positive semi-definite. Okay, so that's the condition here. Suppose HI is affine. Okay, when we say affine, HI, H subscript I, W is of this form. Constant transpose, constant vector, times W plus B. And GIs, the GIs are strictly feasible, meaning there's strict inequality. So it's not greater than or equal to 1, but greater than 1. So there's no equality. Now there exists some values, W star, alpha star, beta star, such that W star solves the primal problem. Okay, so this alpha star and beta star will solve the dual problem. Okay, assuming that we have this quantities W star, alpha star, beta star, and the primal problem is solved by W star, then this condition also holds. So the dual problem is solved by alpha star, the very same values, and beta star also. And also, this condition is satisfied. Okay. So basically, if we want to solve the primal problem, we can also solve the dual problem, because the solutions for alpha star and beta star are going to be the same. Furthermore, we have the following. You can show the following. Okay, I won't show it here, but under these conditions, we have the following. Okay. Well, alpha I must be greater than or equal to 0. And then this constraint, this is the inequality constraint, is also satisfied. Yeah, so these are the conditions. This is a theorem that we had earlier, if you recall. Now there's this additional one, this additional condition. It's called the Karush-Kuhn-Tucker complementarity conditions. So basically, it says that for the solution alpha star subscript I, G of I, W star, so star means optimal solution, the product of this must be 0. Now, let's analyze that. So if you have two quantities and the product of these quantities are 0, what does it mean? Either one of them is 0 or both of them are 0. Okay, any quantity multiplied by 0 gives 0. So if one of them is 0, then the product is going to be 0. And for this to happen, either alpha star or GI would be 0. But usually GI, okay. So suppose alpha I is non-zero, okay, which means that this whole thing is 0. G of I is equal to 0. So when we have this case, we say that, okay, when Gi of W is equal to 0, what we have is an active constraint. That's the case where alpha I is greater than 0. Okay, now let's apply all these concepts to the maximum or the maximal margin classifiers. So our original problem, if you recall, let's go back. Okay, so this is our original problem. Okay, and we want to solve this minimization problem using the concepts that we have just discussed. So remember this, W transpose W, and then this constraint greater than or equal to 1. Now it's the same as W transpose W is the norm squared. Now there's a 1/2 here, but okay, anything, just add 1/2 there, no problem. Okay, you can add any, you can multiply that by any constant, but let's put 1/2 here. You'll see later on why you need a 1/2. Okay, so this is the same as before, but this time it's, oh yeah, it's 1. Okay. Now we rewrite the constraint, the inequality constraint, this one, we rewrite it as this. Okay, so this is now GI WB, right? Less than or equal to 0, because okay, so we move 1 to the other side, okay, and then we invert the sign, multiply it by minus sign here. So this is the same as that. So now let's have some analysis here. Implication of this with respect to the KKT conditions that we saw in the previous slide. This is the KKT condition. When the alpha subscript I is greater than 0, then we said that the inequality constraint is going to be 0, an active constraint. What does that mean? This means that the training example has a functional margin equal to 1 because of equality. Okay? Equal to 1. So, looking at this, when you have alpha not equal to 0, then the margin, this is the functional margin, is equal to 1. Okay? And when it is 0, it is greater than 1. If you think about it, this is the meaning of that. So those alphas with values greater than 0 means that you have these vectors here. These are the examples that are close to the optimal separating hyperplane. So again, when the alphas are non-zero, the corresponding values, the corresponding training example will be active. Okay, and when alpha is equal to 0, you have non-support vectors. So these are the vectors that are non-support vectors, those that are not part of this this boundary. Okay, so that's the interpretation. Okay, so let's solve for those alphas. In other words, how do we compute for these vectors? So there has to be a mathematical way by which we can compute which of these vectors in our training data will become support vectors. So to do that, we have the following. We formulate the generalized Lagrangian. So let's take a look again at our original formulation. This is our primal problem. So the Lagrangian is equal to this plus, so this one, minus rather this quantity here. Okay. What is this? This is your G. This is your G sub I. Right? This is your G sub I. Here, this is your G sub I. Okay? Minus yi, this quantity, plus 1. And that's this one. Okay? Now, so these are generalized Lagrangian. According to Lagrange, the way to solve for the W that will maximize this, that will optimize this, is to set this equal to 0. So differentiate this with respect to W, set that to 0, and solve for that W. So let's differentiate this quantity here. What is the derivative of this with respect to W? Well, it's 2 times 1/2 times W. So that's why we place 1/2 here, so that the 2 will cancel out with the 1/2. Okay, so now we have W here. And for this one, if you differentiate this with respect to W, it will remain this p here will disappear, and this one also, this term here. So what will remain would be alpha y w xi, derivative of that. So the w will disappear. So alpha y xi, which is this, alpha y xi. Remember, we are differentiating with respect to w. That's why this quantity disappeared. Again, this is sum over the values for this for I equals 1 to n. So, what does this mean? Well, w is equal to this quantity here, or w is equal to this. Magic. Magic. W, what is w? W is the one that we were looking for. It's the weight vector. According to this, the weight vector of our hyperplane, or the values that will define our hyperplane, is just equal to the linear combination of the support vectors. Isn't that great? So after all those difficult equations, now we know that w is just equal to the linear combination of the support vectors. And some of the alphas are 0. In fact, most of the alphas are 0. The ones that are non-zero are called the support vectors. Right? So the weight vector is composed of the linear combination of not all the vectors, but only the support vectors, because for the other training vectors, alpha is 0, so you can get rid of them. Again, let's solve for b. Okay, so for b, we have this following. Okay, so differentiate this quantity, the right hand side, with respect to b. So this does not contain b, so this thing will disappear. Now differentiate this with respect to b. What will happen? What we have is this. Okay, alpha y b. Sorry, yeah, alpha y b, and differentiate that with respect to b. So it becomes alpha y. Just this one, and you set that equal to 0 following Lagrange theorem. We have the following quantity. Now let's go back to this. Okay, you plug this expression for w into this original equation. Okay, so this w here and this w there, you replace that with this quantity on the right hand side of this equation. What you have now is this, and this, and that. Okay, so this 1/2 w norm squared is just this quantity here, and then when you plug this quantity here, what you have is this, and you simplify, and what we have is the following. And let us define this as w alpha, w of alpha. Alpha is the vector for alpha I and alpha j. Okay, now so we have transformed our problem into a dual problem. Our original problem is the following. We said earlier that our strategy is to transform our primal problem into a dual problem, which we have just done now here, and then resolve the dual problem. So our dual problem is this. and it should be easier to solve. So we use quadratic optimization software to solve this maximization problem. Now, once we have solved for, first we solve for alpha, okay, using our software, okay, once we have alpha, we can now get the W, and this is what we want, right? W is the weight vector that we're looking for. Then we solve for the bias, the optimal bias value, according to this equation, where here we're trying to find the worst positive and negative examples and split the difference between them. So that way we can get beta star. Okay, so we now have the optimal value of W and P star, which will define our optimal separating hyperplane. That's it. And you might ask, where do I find the software? Quadratic optimization software. Well, in the olden days of SVM, you really have to buy that software from companies. And naabutan ko pa yan, when I was studying SVM. We really can't use SVM because you have to buy the software. So you have to ask for money to buy that quadratic optimization software. And then people said, oh, we don't want that. No, we don't want to be relying on companies milking us. And researchers started working on circumventing this problem, this buying software. So there were several proposals. There was this guy from MIT who did his PhD dissertation in, I think, industrial engineering. So he solved this problem. He solved this problem using chunking, a method called chunking. He became famous. Imagine, if you're able to solve that, you distribute your freeware to the rest of the world. The rest of the world will treat you very well. This guy's name Osuna, I think Osuna, from Venezuela. So he's a PhD student. That was, I think, his dissertation. So he became famous. Not for long, because another guy came up with a better software. Okay, a guy named John Platt from Microsoft, and he released it to the rest of the world. So I don't know how long Osuna's glory was, no? So short-lived glory, no? Because now no one pays attention to his algorithm. Everyone's using SMO or better versions of SMO. So wala na. Imagine you do your PhD dissertation, and then in 1 year, yung pinaghirapan mo ng sobrang tagal na wala na. No? Okay, so ganun talaga. Anyway, so let's now take a look at the SMO by John Platt. So again, let's summarize what we have done so far. We have cast our SVM problem into a convex optimization problem for linearly separable data. This is the primal problem we've seen before, and the dual is the following. Okay, this is what we have in the previous slide. Okay, so we're just previews this one. Okay, so we're just summarizing it here. Okay, maximize this quantity subject to these two conditions. And once we have the W and B, then we can now predict. Simple as that. Okay, so this is the equation for doing the prediction. So we now have linear classifier that is based on sound mathematical principles that will give us the optimal separating hyperplane. Wait, you'll say, oh, but my problem is it's not really linear. No? So what should I do? Back to neural networks, which can give me non-linear decision surfaces. Yeah, you can do that. But Vapnik and colleagues discovered the solution. They call it the kernel trick. The kernel trick is the following. So you have your, this is what you're trying to optimize. So look for the optimal separating hyperplane in input space. But unfortunately, in this case, the input space will not give you the possibility of having a hyperplane, the linear hyperplane. So it's non-linearly separable, your data. What do? This is the magic. And when I was a student, I was very amazed by this magic. And many people were very amazed by this magic. It's called the kernel trick. So the kernel trick is the following. It transforms your linear classifier algorithm, which is what we discussed before, to a nonlinear problem by mapping the nonlinear features into a higher dimensional space where they now become linear. In other words, you do a transformation to your data, and in that feature space, which is now higher in dimensions, okay, is higher in dimension than the input space. The feature space has a dimensionality higher than the input space. Suddenly your problem becomes linearly separable. And when you have a linearly separable problem, you can now use this, because it's true for linearly separable. So what you need to do is just use the kernel trick. And what is the kernel trick? The kernel trick plays around with this quantity here, this dot product, the dot product between your input, this is your input x, and your support vectors xi. Okay, so that's your kernel. It takes advantage of this inner product. Let's take a look at the kernel. Okay, so in our convex optimization problem, we will replace this dot product with this dot product of kernels. In other words, we have a kernel function, and we input that value xi to the kernel function, and we have this value. So then you do that dot product. Okay, so let's have an example of a kernel function. So let's write this as a k of xi xj. Okay, and to simplify matters, and so that we don't get very confused with the xi and xj, let's just simply write x for xi and z for xj. So now the kernel for x and z, which is equal to this, right? It's now equal to the kernel. Okay. The dot product of the kernel of x transpose x kernel z. So this is z. This is a typographical error. Now, for example, n equals 3. Okay, meaning 3 dimensions. N here is 3. So the kernel will just be x1, 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 x2, x1, x3, and so on. Okay, These are the elements of your kernel. Now, remember that here we have how many values? We have 9 values. For n equals 3, the dimensionality of this is 9, right? And if you want to take the transpose of this and multiply it by the same, it will take you O(n) squared time, right? Since the length is O(n) squared, okay? And we need, okay, so that's O(n) squared. And there's a problem because in imaging, the number of dimensions is equal to the number of pixels. How many pixels do you have in a picture? Millions. No? Millions squared. Wow, that's going to take a long time. However, with the kernel, the computation just takes O(n) time to compute. First, we compute x transpose z, then we square it, and that takes O(n) time. Right? Amazing. So that's the kernel trick. That's the magic. Let's have another kernel. Suppose we have this kernel here, and if you do the expansion, this becomes like that, and phi now is equal to this. So what does the kernel do? This is the polynomial kernel with degree 2. It's a quadratic kernel. So you have quadratics and monomials as well as a constant. So this is your this is the generalization for this kernel. This basically corresponds to a feature mapping into a feature space that has n plus d. Choose the dimensions. And the magic of this is that the computation of this kernel takes O(n) time. Why? Well, if this is n dimensions and this is n dimensions, this takes, the product computation takes O(n) time, including the c. And you square it, there's another operation, it's still O(n) time, right? Although you are operating in that very high dimensional space. Okay, so that's the kernel trick. Let's take a look at the kernels. Kernel trick is the following. Basically, you map your x into a higher dimensional space using the kernel. So the feature space now is phi of x. Okay, and similarly here for z. So phi of z. Now the inner product is your kernel. So the first step is to map it. Then you multiply you do the dot product operation. So what is this trying to say? Well, basically, when we do an inner product, what do we do when we have an inner product here? We're basically looking at the similarity between these two values, right? If you have two vectors, okay, when the vectors are perpendicular to each other, that means the dot product is 0. And when the dot product is negative, they're just opposite, pointing in opposite directions. So now if x and z are similar, x and z will be pointing in the same direction, and the inner product will be large. So which means that when the kernel is large, that means that x and z are similar. Or rather, if x and z are similar, this quantity here is large. And if x and z are dissimilar, then the quantity, the kernel value is small. Another property is that a kernel is a valid kernel if the above property is true. Okay, so if you don't have this property, then it's a fake kernel. So don't choose that. It will not give you good results. It will not give you even mediocre results. It will give you poor results. So let K be a kernel and let the training set be provided. Define K to be the kernel matrix so that we have the following. So this is your data, okay, xi and xj. Now for any vector z in Rm, z transpose k z, okay, is equal to the following. And if you include the kernel here and you simplify, what you will notice is that this becomes the following: is greater than or equal to 0. So basically, what does it say? If this quantity is greater than or equal to 0, what we have is a positive semi-definite matrix K here. So that is the definition of a positive semi-definite, right? If you recall your linear algebra. Okay. Now, if K is a valid kernel, the kernel matrix must be positive semi-definite. So this is what we just saw. The converse is also true and is used to prove the validity of a kernel. In fact, there is a theorem called Mercer theorem. This was formulated in the 30s, I think, no? 1930s. There were no computers then, but Mercer already had the mathematical formulation for this. So the kernel K is a valid or a Mercer kernel. That is, there exists a kernel such that a mapping phi such that the kernel is equal to phi of x transpose phi of z. If and only if for all training examples it holds true that the kernel is symmetric, positive, semi-definite. So what is this trying to say? Why do we want a Mercer kernel? Or why do we want our kernel to be symmetric, positive, semi-definite? Semi-definiteness of this kernel matrix is important because this will make our SVM optimization formulation convex. If we don't observe this, then it might be that the SVM optimization problem is now a non-convex optimization problem, in which case we will not be able to get the global optimum. We will not get the optimal separating hyperplane. We will run into local minima. So by imposing this condition of symmetric positive semi-definiteness, we are ensuring that the solution of our optimization problem is a globally optimal one. Now, let's take a look at some of the kernels that are being used by people. So we have the frequently used kernels, the popular ones. You have the linear kernel, which is this, polynomial kernel, where d here is an integer, and we have the Gaussian kernel. So this is the Gaussian. So this kernel is called the Gaussian kernel. And the Gaussian kernel corresponds to a feature space that is infinitely dimensional. In other words, this feature space for the Gaussian kernel, if this is a Gaussian kernel, this is in infinite dimensions. Infinite dimensional Hilbert space. Hilbert space because it's an inner product space. So it's so amazing. So how do we know that it's really an infinite dimensional space? Well, just to do the expansion. So, well, set sigma equal to 1 for simplicity. We don't want to be having lots of messy constants here. Okay, so set it equal to 1. So now what we have is the following. And as you will notice here, k ranges from 0 to infinity. So that shows mathematically that the Gaussian kernel is a projection into a feature space that is infinitely dimensional. Then we have the radial basis function kernel, which is also popular. If you look at the two, they're very similar, and therefore this is also infinitely dimensional. Then we have some more popular kernels. So this is exponential kernel. The only difference between this and the Gaussian is that this one doesn't have a square here. Then we have the hyperbolic tangent or the sigmoid kernel, okay, which is this. So this is actually equivalent to a neural network. A neural network that will generate the optimal separating hyperplane. So an SVM kernel, an SVM that has the hyperbolic tangent kernel is equivalent to a neural network with an optimal separating hyperplane. So it's so beautiful, this theory. And then you have other kernels, not so popular ones, but yeah, here we have a lot more. I've listed up to 26 different kernels. It's just up to you to look up in the internet, look for the appropriate papers for these different kernels. I won't list them down here. I mean, put the formulas here. So, why do we have to bother about so many kernels? Why not just use one of these popular ones? These are the popular ones up to number 6. Okay, the first 6 are the popular ones, frequently used ones. And the rest, you don't even encounter them much. So, but why are there so many kernels? Why not just choose this? Well, the answer is, if you want your problem to have high accuracy, you have to match the kernel with your problem. So can I just pick a particular kernel here and expect your SVM to run with good performance? It will not give you good performance unless you match the kernel to your problem. And since there are many types of problems, then you have many other types of kernels that are available here. So since I don't know your problem, I cannot give you a specific advice. But in general, for most problems, the first 6 ones are already going to cover most of these problems, classification problems. So just try them one by one. Those with experience, of course, will tell you, okay, choose this particular kernel. Again, I cannot overemphasize the fact that your problem has to have the right kernel. If your kernel is not the right one, you might be disappointed and think that your SVM is useless, when in fact you have actually chosen the wrong one. Okay, now, so far we've been talking about linearly separable data, but most of our data is not linearly separable. How do you solve this? We use the soft margin SVM. When we say soft margin, this is our optimal separating hyperplane. This is our data. Okay, and then for some strange reason, this thing here, okay, this blue, this red bubble here, is here in this location, and this green square should be somewhere else, but it's there. Why does this thing happen? Because of outliers, because of noise, because when you do a survey, not everyone is truthful, and because of that, you have fake data points, but you never know which ones are the fake ones. So this causes, of course, nonlinear separability. Okay, so we're now talking about um, nonlinear separability in the input space. Okay, although of course we have the kernel that will solve that. No, but okay, so let's have the case now where we allow data points, outliers, to violate certain to trespass the boundaries of our separating hyperplane. So these are probably outliers, and in fact this should be here and this should have been there, except that they end up in the wrong places because of noise. So we will capture that by allowing a slack. So this is the slack, right? So this should be here at least. At the worst case, it should be here. But then with slack, we allow it to trespass in this for this particular point's size of I, for this point I, and it's for this point J. It even went to this side, no? So malayo na, no? So let's call this value, the distance, the gap, as size of J. So we'll allow that. We will allow some of the points to have some, allow some trespassing in and these are so like fences, okay? But then we allow trespassing, but not too many, no? So now we want to minimize this trespassing, but it's still allowed, okay? And we control that by this value C. So if C is large, then we minimize this trespassing. If this is small, then we are a bit more lax and allow more trespassing. Again, we have the same formulation as before, and we allow trespassing. We have an epsilon I greater than or equal to 0. Okay, so this green here can even be there if you like, because this is size of I greater than or equal to 0. But we have to sum up all this size of I, multiply that by constant C, and we minimize this whole thing here. So there's a penalty term where each training example can be separated by functional margin greater than or equal to 1 minus size of I. Again, just like before, when we have this greater than or equal to 0, we have correct classification. When this is less than 0, we have misclassification. And we allow misclassification like this by permitting size of I to be greater than 0. And however, we cannot just allow any of these to keep on crossing the boundaries, the fence. So we need a penalty term that discourages mistakes. So this is now our new soft margin SVM, and we solve it. Okay, it's the same as before, except now we have this two terms, this term here and this term here. Okay, so this is the additional terms, blah blah blah. Do the same process. Okay, and after some mathematics, the only difference is this. Okay, the KKT conditions are the following. Okay, so that's your dual. You solve that using your optimization software. Then there you go. Okay, now let's talk about the optimization software. So one of the best or most popular SVM implementation is the one by a professor from National Taiwan University. It's called Live SVM. I think it's Live SVM. So it still uses this sequential minimal optimization algorithm. So what is the SMO? The SMO is the following. So we have our optimization problem, which is which is this. Okay, W of alpha is equal to this quantity here. Okay, and that's what we want to optimize. So we want to maximize W of alpha 1 up to alpha n. We assume first that we don't have constraints on the alphas. So if we don't have constraints on the alphas, one good algorithm to use is the coordinate ascent algorithm. What is the idea behind the coordinate ascent algorithm? The idea is the following: we choose a particular dimension, like say we're here. Okay, this is the minimum point, optimal point. We're here. Then we choose say alpha 2. Okay, we fix alpha 2 and then optimize. So when we optimize, we end up here. Then we choose another dimension, alpha 1, we end up there. I choose another dimension, keep on doing that, and we arrive at the minimum point. So the algorithm is as follows. Repeat for I equals 1 to n is the number of dimensions. You basically just take the argmax of this function with one of them fixed. Okay, one of them fixed, and then you change that dimension that you fix each time. So in other words, you hold everything fixed except alpha I. Sorry, I said, yeah, we hold everything fixed except alpha I, the one that you chose, and optimize W with respect to alpha I. Then we alternate between alpha 1 and alpha 2 if we only have 2 dimensions. For large dimensional spaces, you just randomize, you just choose any one of these each time. Okay, and then you arrive at the answer. Now for high dimensional spaces, usually have more iterations than Newton's method. However, the evaluation of this is very fast. So since this is very simple, the advantage of this is that it is easy to evaluate or inexpensive to evaluate. So that's the coordinate ascent algorithm, which, by the way, will not work for SVM because we have constraints. So we said that this will work if we don't have constraints. So what do? Well, we modify it a little bit. We only change 2 alphas at a time instead of 1. Here we change 1 alpha at a time. Hold everything fixed except alpha I. But here we change 2 alphas at a time. So this is the SMO algorithm by plot. So the outline of the algorithm basically is the following. We select alpha I and alpha j using some heuristic. And then we hold everything else except alpha I and alpha j. And then we optimize W alpha with respect to alpha I, alpha j, subject to all constraints, such as, for example, the Karush-Kuhn-Tucker conditions. Now, okay, we know that this is equal to 0. Okay, so now say we have alpha 1 and alpha 2 lang, no? So for simplicity, just have alpha 1 and alpha 2 as the target variables. And since this is equal to 0, alpha 1 y1 plus alpha 2 y2 is equal to the negative of everything else, I equals 3 to n, for this to be equal to 0. Right? And we call this quantity here as psi. And the second constraint is that alpha I is between 0 and some constant c. Now, for constraint 1, alpha 1 y1 plus alpha 2 y2 is equal to psi will give us the following. So just a little bit of algebra will give us alpha 1 is equal to this minus alpha 2 y2 over y1. So that's now the formula that we will use from this constraint. Now the second constraint is called the box constraint because we want our alpha 1 and 2 to be within this 0 to c and 0 to c. So we want our alphas, our point, to be inside this box, 0 to c in one dimension and 0 to c in the other dimension. So now, so this maximization, or this quantity that we want to maximize, will be formulated as the following. So this is alpha 1, right? That's alpha 1 and alpha 2 is there. And then all the other alphas are held constant. So now our W will take this form. So it now will be of the form A plus A times alpha 2 squared plus B times alpha 2 plus C. So this is a quadratic formula which you can now use. We can use the quadratic formula rather to solve for alpha 2, right? So alpha 2 can be expressed in terms of B and A and C. Okay, so we can now optimize this using the quadratic equation. Okay, so what we have here is this point here. So when you have a quadratic, let's see, where's the pen here? Okay, when you have a quadratic function, it goes like this, right? Ganyan, you know. So now if you have a quadratic, so this extends, by the way. You're just following the box constraint. Now if you have, for example, this quadratic equation, and your point, the solution to your, okay, this is your minimum point. Remember, this is a quadratic equation, right? So this is the minimum point. It's outside the box. What do? You set it to this point. So since it's outside the box, you put it here. You transfer it here for your next iteration, because if you retain this, you'll be violating the constraint. However, if it is within this constraint, like this quadratic equation here has this minimum point here, that's fine. Okay. Okay, so let's show a quadratic equation there. Okay, so you keep on doing that. This is called clipping. Clip if necessary, and that's your SMO idea. Now, how to choose alpha I and alpha J as well as B, I encourage you to read Platt's paper. Okay, but it's important for you to know this part here. And that for SMO, we are using just this alpha 1 and alpha 2, or alpha I and alpha J. Okay, so references. The one in Platt is important. Okay, so this is paper here by this author. Now, if you are interested in kernel functions, you may refer to this blog. Um, it tells you the available kernel functions for machine learning applications. There are also other papers on that. So if you're doing working on some non-imaging problems, then you have to do a good research to extract the best from your SVM by using the right kind of kernel. That we end our lecture for today.